Good evening, everybody. Today we have discussed the Nernst equation. Nernst equation is used for finding out the potential of a half cell or a electrode or a reversible reaction or a cell. So first of all, we are discussing the how we will measure theoretically the potential of a half cell. So for the Nernst equation, we have to always write any equation in terms of reduction. So consider a metal atom. You know that the metal always loses its electron to the other element. But even then, we have to write that equation in terms of reduction. So consider M is the metal and it is exists in the oxidation state of N plus. So we have to write the equation like this: M N plus N electron gives M. So the Nernst equation for this half cell is, that means half cell means an electrode of a metal which is dipped in its salt solution. So the potential of that half cell is calculated theoretically by this Nernst equation. E, that is the potential of that half cell, that's equal to E0, that is the standard potential of that half cell, minus 2.303 RT divided by NF into log 1 divided by metal to the power N plus. See here, the log 1 which is representing the molar concentration of the M, but if the element is taken in the elemental state, that's why we have to substitute the concentration of the M, that's equal to 1, that is activity. So substitute log 1 divided by M to the power N plus. Then we know that R is a universal gas constant, T is the temperature in a standard state, and F is the Faraday. So if we substitute this value, we will get this, our equation become E is equal to E0 minus 0.059 divided by N into log 1 divided by Mn plus. So this is the Nernst equation for the half cell. Then we can apply the same Nernst equation for a chemical reaction. We know that in a chemical reaction we have the starting material and we will get a product. So for writing the Nernst equation, we should always keep in mind that log, instead of the element we have to substitute the product divided by the reactant. So our equation become E electrode, that's equal to E0 of electrode, that means potential in the standard condition of that electrode, minus 0.0592 divided by N into log product divided by reactant. So this is the Nernst equation for the conversion of the aluminium to its aluminium ion. That means Al3 plus 3 electron gives Al. So how we will write the Nernst equation? E of Al3 plus gives E0 of Al minus 0.0592 divided by 3 into log 1 divided by Al3 plus. Okay, then while we are rearranging Al on the numerator, we have to convert this plus sign into minus sign into plus sign. Now, how we will write a chemical reaction? We will write a Nernst equation for a chemical reaction. See here, this is the galvanic cell. Galvanic cell means zinc rod dipped in zinc sulfate solution and copper rod dipped in copper sulfate solution. So the overall reaction is Zn plus Cu2 plus gives Zn2 plus Cu. So how we will write the E cell and how we will calculate the potential of this cell? For that we have to apply the Nernst equation. So E cell is equal to E0 of cell minus 2.303 RT divided by 2F into log. Here the product is Zn2 plus into copper divided by Cu2 plus into Zn. So we know that the activity of Cu is 1 and Zn is also 1. So our equation become E cell is equal to E0 of cell minus 2.303 RT divided by 2F into log Zn2 plus divided by Cu2 plus. Next, we are moving into the reference electrode. We know that we cannot measure the potential of a half cell. So one of the method for measuring the potential is to convert that half cell into a cell by clubbing with some of the electrode having the known potential. So that electrode is known as the reference electrode. We have already studied the hydrogen electrode, and we are also studied how we will measure the potential of the other electrode by using the hydrogen electrode by clubbing this hydrogen electrode. Next, we are moving into the next reference electrode, that is the calomel electrode. So usually the reference electrode can be divided into the two different variety. First is the primary electrode, the second one is the secondary electrode. So the example for the primary electrode is the hydrogen electrode. But you know that the maintaining the hydrogen electrode is very difficult because we have to pass the hydrogen gas always till the for a long time. So it is very difficult. So we are usually using calomel electrode as a reference electrode in the laboratory. So calomel electrode, the symbol representation of the calomel electrode is like this. The bottom of the test tube, bottom of the tube, we have a mercury, and above that we have mercury chloride and mercury paste. Above that we have a solution of the KCl solution. So depending upon the concentration of the KCl solution, the potential of the calomel electrode vary, and in the middle we can see a platinum wire. This is the representation of a calomel electrode. Then if you are filling the KCl with a saturated solution, the potential of the calomel electrode is 0.2444. If it is a 1 normal solution, then the potential is 0.289. If it is a zero point 0.1 normal solution of the KCl, then the potential of the calomel electrode is 0.3356. So what is the chemical reaction occurs in a calomel electrode? Calomel electrode, usually the Hg2 plus receive the electron and we will get an Hg, and this reaction exists in an equilibrium. Then overall equilibrium is expressed by Hg2Cl2 plus 2 electron gives Hg plus 2 Cl minus ion. So the mercurous chloride and mercury are at a unit activity. Therefore, the electrode potential can be written as E calomel is equal to E0 plus RT by 2F ln 1 by A Cl minus ion. Okay, thank you.